Welcome back. So, we are at the point of the class now where our cosmic zoom lens, which has been fairly tightly focused in on things, astronomical things like the sun and star clusters and stellar evolution and individual things in the Milky Way galaxy. We are now going to start at an more rapid rate, expanding that cosmic zoom lens out and thinking about bigger and bigger structures in our universe. And we'll start our study of cosmology, the study of the universe itself, by talking about one of the galaxies that we know the most about, our home galaxy, the Milky Way galaxy. So let's, why do we call it the Milky Way? What is it? How does this work? Well, let's take a look. We saw in today's astronomy picture of the day, here's another beautiful view that shows a little better what the disk of our galaxy actually looks like from our vantage point on Earth. If you have never been to, if you've never seen the Milky Way galaxy, you owe it to yourself to take a warm summer night this evening, find a spot that is way away from city lights if you can, take a friend, and just lie out on a clear night and take a look. And if it is dark enough in the area that you are, you will be able to see what first kind of look like clouds in the sky, but these aren't actually clouds in our atmosphere. These are clouds in the disk of our galaxy itself, and you can kind of see it all laid out here. There's a comet here too. You probably won't see that one, but you can kind of make out, this is an all sky fisheye view. So this kind of looks like a curved path, but this is actually a straight line. And you can kind of see the disk laid out right here. And you can see right here, the center of our Milky Way galaxy. And you can see it kind of bulges in the middle, and the disk of the galaxy is thinner than it is at the very center. If you could, obviously we can only see half of the sky at one time when we're standing on Earth, but if you take multiple images of the sun, of the sky, taken at different areas, and stitch them all together into a single image, you get something that looks like this. This is again, there's no way to take, well, the sky is a spherical thing, just like the Earth is a spherical thing. There's no way, just like there's no way to make a flat map of the Earth that doesn't distort things, there's no way to make a flat map of the sky that doesn't distort things. It's just the inside of a sphere instead of the outside of a sphere. It's the same problem though. And so this is a typical view that you'll get of the entire all sky view of the galaxy. And in this particular thing, you'll notice there's an ellipse, which is the shape of the projection itself. And it's typical to show an all sky view, especially when we're thinking about the galaxy, in one that puts the area of least distortion in the middle, and that's the region that we want to see the most, and that's the disk of the Milky Way. And if you put the center of the Milky Way in the center of the image and the disk along the major axis, then you get the least distortion in the regions that you're most interested in looking at. And so we'll see a lot of these in the next class or two. So this is sort of what it is that we're looking at, an all sky view that shows the disk of the Milky Way galaxy, this time all the way from one end to the other. And again, this is the center of the galaxy. This point connects with this point. They're the same point, exactly 180 degrees opposite of this point. So you can see now the Milky Way, and you can see the kind of the different components that make it up. You've got a disk, you've got a bulge, and you've got some other things around here as well. So that's the actual view of the Milky Way. It's usually better to see some cartoon versions just to see what's going on. So let's talk about the structure of the Milky Way. You ready? You've got the creamy nougat, the chewy caramel, and of course, to top it all off, the rich milk chocolate. Okay, I apologize. That's not the Milky Way galaxy, that's the Milky Way candy bar. Makes you hungry though, doesn't it? Okay, let's talk about the structure of the Milky Way galaxy. Haha. So again, components. This is again the cartoon version of the actual view that we saw before. There is what we think is a fairly thin disk. 1,000 light years thick or so, which seems thick, seems pretty large, but on the scale of the galaxy, it's not that much. There's a bulge at the center where it seems to be more of a less disky thing. And here's our location about 28,000 light years from the center of our own galaxy, which is almost 100,000 light years from side to side. If you know your Monty Python song, you can sing along. If you don't, look it up. It's pretty cool. Again, the disk, the bulge, this is the disk, the bulge, the halo, which I haven't really talked about, but the halo is a spherical distribution of stuff that goes all the way around and encompasses and even, and then some, the disk of the galaxy, but is more of a sphere. And globular clusters are members of the halo of the galaxy and not the disk of the galaxy. If we could take a rocket ship and go up above the disk of the Milky Way galaxy and look down on it, it might look something like this. You could see that the disk of the galaxy is not just a uniform distribution of matter, but in fact, probably the matter is distributed in several spiral arms. Again, this is kind of an interesting game that you have to play when you're studying the Milky Way galaxy, because it's hard to get you can't get this view of the Milky Way. It's impossible. It is, the analogy I like to make is it's kind of like trying to measure or discover, so you live in a glass house, you're trying to discover the nature of the glass house that you live in, but you're stuck in one room, right? And so you can kind of infer other rooms in the house, but there's furniture blocking some of it and you can't even see all of it. But you can look out and see other glass houses on the block and make inferences about what your house looks like based on what those other, even though they're farther away houses, actually look like. Because we can't get this view of our own Milky Way galaxy because we're in the middle of it. Okay, so the story of how we know where we are in the Milky Way is an interesting one, and the story goes back all the way to the 1700s. There was a British astronomer named William Herschel who built what were the best telescopes in the world at the time, and the biggest and the best telescopes in the world. And he used them to do lots of interesting things. Among the interesting things that he did, and in fact, many of the named nebulas that we have come from William Herschel and his diagrams, that his drawings of them. This is way before photography. And why do we call the Crab Nebula? Well, when William Herschel went and drew a picture of the Crab Nebula, it kind of looks like a crab. And so I'm not sure it was he or someone else who dubbed it that, but that's where a lot of these names come from. Anyway, one of the things he did was try to figure out where we were in the Milky Way. He knew that there was a distribution of, he could see that disk of material, and he wanted to know, well, we must live in this disk of material. The sun and the planets must be here. Are we in the middle of the disk? Are we on the edge of the disk? Where are we? And he went about doing this by counting stars, right? So he took a particular direction in the disk, and he counted all the stars he could in that particular direction, and he got a certain number. And then he went a little bit over and looked there, and he found a different number and a different number. And so he figured that if we were in the center, that we would see the same number, roughly the same number of stars in all directions. And if we weren't in the center, there should be a direction where we see more stars and a direction where we see less stars. This is the map that he made. So here we are in the center, and this whole thing is filled with stars, as you can see, but the distance from the center to the outer star is proportional to the number of stars that he measured in that direction, right? So look at this map that he made. It kind of looks like there may be some interesting things going on in this direction, and maybe that the galaxy is somewhat elongated and it's got some weird structure, but he came with the conclusion that we're pretty darn near the center of the galaxy. Now, he was terribly wrong. Why was he terribly wrong? Well, he didn't really understand how this works, first of all, but he also didn't understand that, let's go back to the actual picture. Oh, there's our Milky Way bar. Back to actual picture of the Milky Way. When you look at any particular direction, you'll notice that there are regions where that's very patchy and regions where it's fairly clear and open. And if you notice those two kind of fingers that poked away, those were in the direction of the center of the galaxy, one of them there and one of them there. And so all he was really measuring was how much dust there was blocking our view of distant parts of the galaxy. We can't actually see the other side of the galaxy because there's this dark, dusty stuff in the middle in the way that's blocking our view. So it was an interesting exercise for him to do, but all he was really doing was measuring how much extinction, how much of this dark dust there is blocking the light from getting through. So it wasn't a very good, it wasn't a very accurate measure of the Milky Way Galaxy. He didn't get anywhere near the edge of the Milky Way Galaxy by doing this because we're surrounded by these dark clouds. And he did, in fact, find these two windows where you can kind of see towards the middle of the galaxy. Go back to show you those. There's our Milky Way bar. That's this arm and this arm. So the center of the galaxy is way off here to the right somewhere in this particular direction. Okay, so how did we discover, who did discover, and how did we discover the true extent and of the true extent of the galaxy, one, and two, where we are in it? Well, you have to go all the way, hundreds of years later in the 1910s, and a guy named Harlow Shapley was interested in globular clusters. Remember, globular clusters are in the halo of the galaxy, so they are above and below the plane of the galaxy, so you can see them a lot more clearly than you can things that are in the disk of our galaxy. And so he was able to, we'll talk about how he was able to measure the distances to these globular clusters, but basically our library variables are standard candles. There's a way to know how luminous they are. And if you know how luminous they are and you can calculate and you can measure how bright they look, that gives you the distance to those galaxies. And so he took all these galaxies, he found these kinds of variable stars in these globular clusters. He measured the distance to those globular clusters. And if, let me pull up my whiteboard. There it is. So, so let's say here's us. I'll draw us as blue in the middle. There's the Earth. And he went about measuring globular clusters. He noticed that there were more globular clusters in one direction than the other direction, and that gave him a clue, but he really wouldn't know unless he found the distances. And sure enough, when he went and measured the distances, I'm just going to draw some random points here. They were not only not centered on the Earth, they were much pushed off in one direction preferentially. And that not only told him that the Earth and the Sun are not at the center of a galaxy. We can draw the disk of the galaxy in here. It might look something like this. It told him, because he knew the distances to all of these, about how far we were to the center of the galaxy. And so he could measure the extent of the galaxy and measure where we were in the galaxy and measure roughly how far we were from the center of the galaxy. Once you know the distances to something, you can start making maps like this. Okay, so what are the kinematics? These different parts of the Milky Way, we've talked about the disk of the galaxy, we talked about the bulge of the galaxy, we talked about the halo of the galaxy, all have different kinematics. And by kinematics, I just mean motion, how they move about the galaxy. Because again, all of these have to be moving about the galaxy. There is some, again, force of gravity is at play here, holding all this together. But if an object weren't moving, it would just fall straight toward the center and actually come out the other side. There's no actual thing there unless it happened to fall right into the center. But that's not what happens most of the time. Most of these are in various orbits about the center of the galaxy. So in the disk of the galaxy, one of the things that characterizes it is all of these stars are moving, orbiting the center in the same direction. And you can see this yellow It's a fairly ordered, they almost all have perfectly circular orbits, very low eccentricity. They're all orbiting the same direction. It gives you this nice coherent structure and shape to the galaxy itself. You see this sort of yellow path. That's a disk, the path of a typical disk star as it moves through the galaxy. And you can see it moving up and down, and that's probably a real phenomenon. As if it moves below the galaxy, it feels a slight gravitational tug up the galaxy. But this is greatly exaggerated how much that actually happens. It doesn't actually, most stars won't be moving above and below the actual disk of the galaxy. It'll be much smaller than that. But that's the general shape. Now, the bulge, there is no preferred direction of orbit. There's no preferred eccentricity of orbit. It's sort of like a random hive of bees, right? All circling in random directions and in random eccentricities and in random directions in the center of our galaxy. And the halo is exactly the same. There is no preferred anything. There's no preferred direction of rotation. There's no preferred eccentricity. There's no preferred direction. These, again, globular clusters in the halo of the galaxy are moving in all kinds of different crazy directions with respect to one another. There's no pattern to it, which makes for a nice spherical distribution like this. Okay, I'll stop there and we'll talk about what the galaxy looks like in other dimensions and in other wavelengths in the next video. Stay tuned.